Solve each quadratic inequality. In this first example, we have 3x squared plus 9x less than 0. We're searching for all values of x that make this statement true. The terms on the left can be factored. Specifically, we can factor out a 3x. If we factor out 3x, we have 3x times x plus 3. In our next step, we're going to identify key numbers, and these will be the cutoff numbers for our open intervals, for which some will contain the answers to the problem and others will not. Our first factor, 3x, when we set it equal to 0 and solve, we get x equals 0. When x plus 3, the other factor, is set equal to 0 and we solve, we get x equals negative 3. Sketch a number line and plot your key numbers on it. And then in the open spaces between the key numbers and outside the key numbers, you will pick test numbers. They can be any value in the open interval. Just try to keep it simple so that your calculations are very manageable. You can either substitute your test numbers into the original statement or into the factored statement. It is totally up to you. In class, you guys told me to use the factored statement, so that's the one that's highlighted in blue. I picked a number less than negative 3, and I chose negative 4 as a test number. Substitute negative 4 in for x in your factored statement. 3 times negative 4 times negative 4 plus 3, that's negative 12 times negative 1, which is positive 12. That is not less than 0. That's a false statement. So this open interval with this test number does not count. We pick a test number inside between the key numbers, negative 1. Substitute that into your highlighted statement. We got a value of negative 6, which is less than 0. That gave us a true statement, so we're going to keep all the numbers between the key numbers. So everything from negative 3 to 0 is part of your solution set. And then finally, test to the right of your larger key number. We randomly picked a 2. Sub that into your highlighted statement. 3 times 2 times 2 plus 3, that's 6 times 5, which is 30. And that's not less than 0. So the only open interval that gave us a true statement was the open interval between negative 3 and 0. In the second example, we have x squared less than or equal to 36. So ultimately, we're searching for all numbers such that if they were squared, the result would be less than or equal to 36. With quadratics, I like to put everything on one side, so I'm going to subtract 36 from both sides. That gives us x squared minus 36 less than or equal to 0. That's a difference of 2 squares, so you can factor with x plus 6 times x minus 6. The key numbers are the values that make your factor 0, so we have negative 6 and positive 6 as our key numbers. As we did on the last example, pick a test number from each interval between and around your key numbers. So to the left or smaller than negative 6, we selected negative 7. You guys told me to use this line for our substitution. Any of these top 3 lines are perfectly okay. Negative 7 squared minus 36, that's 13. That's not less than or equal to 0, so we get a false statement. The test number between the key numbers we picked was 0. Subbing that into the purple highlighted statement, 0 squared minus 36 is negative 36. That is less than or equal to 0, true. We're going to keep this interval of numbers. And then finally, testing the third interval, we used an 8. 8 squared minus 36, that's 28, which is not less than or equal to 0. The only interval that gave us a true statement was between the key numbers. Because our inequality is also underlined, we include the key number. So we'll use brackets instead of parentheses. In our third example, we have x squared minus 8x plus 2 less than 11. Subtract 11 from both sides. X squared minus 8x minus 9 less than 0. Factor x plus 1 times x minus 9. Remember when you're factoring that the sum of these two numbers give you the middle value, and the product of these two numbers give you the third or constant value. Setting each factor equal to 0 will produce your key numbers. This first factor is equal to 0 when x is negative 1. The second factor is equal to 0 when x equals 9. Those are our two key numbers. Testing between and around the key numbers, we chose negative 2, and you guys wanted me to use the original statement for this one, so we plug them in. Negative 2 into the highlighted statement. Negative 2 squared minus 8 times negative 2 plus 2, that is not less than 11. So that's a bad area of numbers. Between the key numbers, you guys wanted me to check with a 0. 0 squared minus 8 times 0 plus 2, which is 2. That is less than 11, so that's a good area. We're going to highlight it. And then our third area, we tested with a 10 and put it back in the original problem. 10 squared minus 8 times 10 plus 2 was 22, and that's not less than 11. So the outer intervals are false. The inside interval was true. The original inequality is not underlined, so we use parentheses, and our solution interval is the open set negative 1 to 9. In our next example, we have x squared plus 6x greater than 7. Subtract 7 from both sides, and that gives us the inequality x squared plus 6x minus 7 greater than 0. Factoring, we factor with an x plus 7 and an x minus 1. 7 plus negative 1 is 6. 7 times negative 1 is negative 7. So this is correctly factored. The first factor is 0 when x equals negative 7. That's a key number. The second factor, x minus 1, is 0 when x equals positive 1. That's the other key number. Picking test numbers between the key numbers and outside, we randomly picked a negative 10. You guys asked me to use this third line, so we plug a negative 10 in for x. Negative 10 plus 7 times negative 10 minus 1. That's negative 3 times negative 11. Well, that's greater than 0. That's true. So we shaded this first interval of numbers. We picked a test number between the key numbers, 0. It's very easy to work with. Substituting in 0, 0 plus 7 times 0 minus 1. That's a negative 7, which is not greater than 0. The middle interval fails. The right interval, 2, is our test number. 2 plus 7 times 2 minus 1, that's 9 times 1, that is greater than 0, so this outside interval is also true. Since the outside intervals give us the true statement, our solution is made up of both intervals of numbers, so we have to unite those separated intervals because both of them together make up the solution set. This left interval, which is all the numbers less than negative 7, is written negative infinity to negative 7. The right interval of numbers, any of them greater than 1, is the interval from 1 to positive infinity. We put a union symbol in because we have two separate intervals of solutions that are not connected, but both of them make up the entire answer. And in our last example, we have x squared greater than 2x plus 3. Getting all terms moved to one side, we subtracted a 2x and subtracted a 3. That moved them all over to the x squared side. And then because we emptied out the right side, that's greater than 0. Factoring, x plus 1, x minus 3. Positive 1, negative 3 has a sum of negative 2 and a product of negative 3. The key numbers are negative 1 and positive 3. Those are the values of x that zero out each factor. Plotting -1 and 3 on a number line, picking test numbers between and around those key numbers, and we substituted into this factored part. So testing with a -2, -2 plus 1 times -2 minus 3. That's -1 times -5. That's greater than 0. Testing the middle interval, 0 plus 1 times 0 minus 3. That's not greater than 0. That's a bad interval of numbers. Finally, you could pick like a 4 or 5. I just randomly picked a 7 in class. 7 plus 1 times 7 minus 3. That's 8 times 4. That's definitely greater than 0. Again, if the outer intervals make up your solution, then the first interval, all numbers less than -1, or the outer right region, any number greater than 3. Both of these intervals make up your solution set, but we have to unite them because they're two separate intervals of numbers. We use parentheses if the inequality is not underlined. If the inequality is underlined, then we use a bracket at the key numbers.